Texas Instruments Innovation Challenge India Analog Design Contest 2014. Project title Solar Powered Electrochromic Shield Protection for Helmet. Faculty Mentor Mrs. Rohini S. Halikar, Assistant Professor ECE RVCE. Team members Akhil Jain, Chetan, Abhishek GR. In the current era of silicon technology, battlefield machines, weaponry, and armors are getting sophisticated with each passing day. However, in spite of an unparalleled mechanical innovation, a soldier finds himself stranded in a battle zone, having to take aim at the enemy against the glare of the sun. Exposure to direct rays of the sun can cause temporary blackouts for a few seconds' time, sufficient to cost him his life. There exists no lightweight, low-power solution to aid a soldier in providing an unobstructed view of the surroundings. Visibility is also a primary requirement for safe driving. In the recent years, many riders have complained of blinding glare emitted by vehicles coming from the front, from behind, or from both directions. The effect of glare is same whether it comes from sunlight or other man-made sources of light. It deteriorates driving performance, resulting in crashes and at times fatal accidents. The current solution involves tinted screens which remain colored even in low-intensity lights, providing an obstructed view of the surroundings unnecessarily. We intend to harvest a relatively new concept of electrochromism to solve the problem of glare. Electrochromism is a phenomenon displayed by some materials of reversibly changing color when a burst of charge is applied, that is, when a voltage is applied. Solar panels. The design makes use of two solar panels, each of 3 volt 200 mA peak rating, to be placed strategically on the helmet to charge a 3.7 volt lithium-ion battery used in the design. Although the system is centered around the protection against high-intensity light, it efficiently uses the same to power the electronics involved in the design. Light-dependent resistor (LDR). The sensor used for determining the intensity of incident light on the helmet screen is a light-dependent resistor. This is used in a voltage divider circuit with 20 kΩ resistance and a potentiometer. The voltage across the LDR is proportional to the intensity of light incident on it. The output of the sensor is fed as an input to the microcontroller unit MSP430. Buck boost converter TPS 63000. In case of insufficient charging current from the panels, the buck boost converter TPS 63000 compensates for the additional current requirements of the lithium-ion battery. The 3.7 volt lithium-ion battery serves as a power source to the design, thereby making it portable. MSP430G2553. In our design, we utilize the built-in 10-bit ADC of MSP430 to convert analog data from the sensor to the corresponding digital values. There is a minimum intensity of light required for seeing objects, which is determined by the Weber-Fresnel law. If the intensity of light is within comfort range, the MSP430 turns on analog switch 1 TS12A4517, which connects ground to the ITO film, which makes the electrochromic shield remain transparent, providing a clear view of the surroundings. If intensity of light exceeds the comfort range, the MSP430 turns on analog switch 2 TS12A4517 while simultaneously turning off switch 1. This configuration connects the shield to the output of the LDR, allowing the ITO film to change color in accordance with the variation of the intensity incident on the same. Potentiometer. The comfort levels of light intensity tolerance varies from person to person. Our system, through the use of a variable resistance, allows the user to change or set threshold levels based on their personal comfort range. This provides our design a unique advantage over the conventional photochrome-based systems, which do not take into consideration the Weber-Fresnel parameter, thereby changing color even in low-intensity light and hence blocking vision in an already dim area. The intensity of light at which the thin film can turn on can be set by the user by varying the potentiometer based on their comfort level. LM324 Quad Operational Amplifier. This IC is utilized in our design to provide impedance matching between the analog switches and the output, which is the ITO film. A switch is provided to turn on or turn off the system.
Chemistry segment. The foundation for electrochromism is a transparent conducting substrate. One such substrate is indium tin oxide, which can be deposited on an insulating surface to make it conductive. The basic requirement of the system is a color-changing material. One such low-cost, non-explosive material is Prussian blue. Prussian blue is a dark blue pigment with the idealized formula Fe7CN18. By the application of electrolysis, Prussian blue can be deposited on the ITO film. One of the simple procedures to do so is as follows. Add 5 ml 0.05 molar HCl, then 10 ml 0.05 molar K3FeCN6, and then 10 ml 0.05 molar FeCl3.6H2O to a 50 ml beaker. Face the conducting side of the screen towards the graphite electrode. Connect the negative lead of the voltage source to the conducting screen and the positive lead to the graphite electrode. Dip the electrodes into the solution prepared above and quickly adjust the voltage to produce 40 microamps per centimeter square for 60 seconds. Rinse the electrode with pure water. Approximately 50 nanometer coating after 60 seconds of deposition can be seen by eye on the conducting surface. The thin film remains transparent with no voltage is applied and change color on application of voltage. Intensity of color is proportional to the applied voltage.
The thin film is to be integrated on the helmet screen. However, to comply with the law which prohibits the use or ownership of chemicals outside educational laboratories, stage 2 of the testing is performed using light emitting diodes, which imitates the color changing property of the thin film. Currently, the intensity of light incident on the helmet is low, hence the thin film is in its off state, that is, it is transparent. As the intensity of light incident on the helmet increases beyond the threshold value, the thin film changes its state from transparent to blue. The color of the thin film is a function of the incident light and it blocks high intensity light to provide unobstructed view of the surroundings accordingly.
We would like to extend our gratitude to Dr. M. Uttara Kumari, Professor and HOD, Electronics Department, for granting permission to utilize the laboratory services in the Electronics Department. We would like to thank our mentor, Mrs. Rohini S. Halikar, Assistant Professor, ECE, for her invaluable guidance during the implementation of our project. We would like to thank Dr. K. Natarajan, Professor and HOD, Department of Chemistry, for granting us the permission to perform the deposition of Prussian blue on the ITO film. We would like to thank Mr. R. Mahesh, Assistant Professor, Department of Chemistry, for guiding us through our trials in the chemistry lab. We would also like to thank Ms. Ishita, Media Department, for guiding us through the preparation of our video demonstration. Thank you.